Hello, good afternoon, everyone. My name is Maria Victoria. I am a young researcher here at IAG-USP. First of all, I would like to apologize for the delay. We have a small inconvenience, but we are grateful that we could solve it. Welcome again to another astronomy department seminar. And thanks for waiting and for being here in Google Meet.
Hello,
or through the YouTube.
My name is Maria Victoria. I am a young researcher here.
Today we have the pleasure of having Professor Adam Burrows from Princeton University. Many thanks, Professor, for being here with us, for sharing your research.
My pleasure.
Professor, okay. Professor George here from our institute is going to briefly introduce Professor Burrows before his talk. So I will ask you, everyone, please, from this moment to turn off your cameras and your microphones. And if you have any question, please express this in the chat, either in the Google Meet or in YouTube. And the questions are going to be asked at the talk. So, George, whenever you want, you can start with the introduction.
Your microphone is muted, George.
George, your microphone is muted.
That's it. Okay, so now you hear me. When I speak about nonsense, everybody listens. But anyway, Adam has been so kind in these hard times to present us an update of a very important and timely subject. I would like to remind his back to Princeton in his graduate stage a long time ago. But anyway, and he also did his PhD work in MIT. And after all, for all his 40 years, he had been contributing to this stuff of understanding how supernova explodes and many other things, including exoplanets, brown dwarfs, and theory, and many other things. He was extremely excited when 1987 blew up, and so this is something that we always tell them, the students, that it's something once in a lifetime. We have seen a real event and done all sorts of calculations pop up, and over the years, and I believe it will be his talk today, trying to understand the effects of hydrodynamical instabilities plus neutrino physics plus fundamental processes and so on. I had the pleasure to be a year with him and his people there in Tucson, Arizona, and UFA. But now eventually he, got melted by the 50 degrees or so and returned to Princeton to do the same stuff, but northern. And therefore, I would like to give him the word and thank again for his disposition to talk us about supernova theory, how it evolved in the last decades, and what's going on right now. Thank you, Adam. Go ahead.
My pleasure. Thank you, Jorge. Now let's see if I can get this thing going. I think in a window or just the entire screen. And share. I need to be able to share. Evidently, something is holding that up. Okay. All right. Sharing, and now do this. Oops. That. How does that look?
It's great.
Is that up?
Great.
Yes.
Okay, it's good. Thank you. Okay, there's a lot to cover in this subject, which is a pedigree of about 60 plus years. I haven't contributed during that entire time, but it seems as though it's been a long time before we've really been able to understand the following problem, which is at the endpoint of the evolution of a massive star, maybe more massive than 8 solar masses, the core achieves what's called the Chandrasekhar mass and becomes unstable. It collapses then after 10 million years of evolution within less than a second to nuclear densities. It rebounds and a shockwave is produced. And for decades, we've been trying to figure out how to maintain the explosion that is that shockwave, because in most of the earlier simulations, things stalled. And so what I'm going to present today are some of the latest results from our group that involves the people that are listed here, supported by the funders on the right-hand side, of the simulations in 3 dimensions predominantly of core collapse supernova explosions. Okay. Okay, so everybody has everybody's name. Okay, good. So this is just a snapshot. And again, I'm going to be going fairly fast. I apologize in advance, and people can ask questions at the end or during the talk if they like, but things will go fast. Not to scale is what's happening. You have a progenitor star at the top. That is the onion skin structure of nested elements from low Z to high Z in the center. This central object becomes unstable and collapses fairly quickly at the end of the evolution of a massive star. When it achieves nuclear densities, which is amazing but true, the material stiffens and a shockwave is formed. It moves out. But in the early simulations, and in particular in spherical symmetric simulations, that shockwave stalls into an accretion shock. And it continues to radiate neutrinos, it continues to accrete, but that's not an explosion. And what we want to do is to understand how this object, which we know has to explode the majority of the time, because this is what we see statistically in astronomy, actually does explode. This is a time lapse of the supernova 1987A, referred to by Jorge in the introduction. And I want to just call your attention to the fact that over that period of time, the object that was created in the center was not spherically symmetric. This is a crude distribution of the matter in the interior, or the light in the interior, but it implies that, in fact, it's asymmetrical. And there are many indications of that among this class. Here is the Cassiopeia A supernova remnant in X-rays, where the different colors are different elements. And you can see that those elements are sprayed out asymmetrically, and that though there is some sort of crude spherical distribution, much of the matter is not distributed spherically. This is also a distribution of the same supernova remnant. This is just an example, one of many, but a very interesting one, again, of Cas A, but in radioactive titanium, which is produced during the explosion, and hot iron on the left-hand side. And it just shows that those elements are distributed aspherically. This is what we're getting now as a still for the supernova simulations, where you have bubbles, blobs of material. This is isosurfaces in entropy, colored by the electron fraction, which is a composition variable, the number of electrons per baryon, and with some representative velocity vectors or streaming material coming in. From the outside, you see it's accreting in, it goes through the shock wave, and then it becomes embroiled in the convection in the interior. And I'll show a lot more of that later. I'm going to show some words first. This isn't going to be eye candy, but it's going to summarize the basics. And the basics are, again, as I say, you have a Chandrasekhar core that collapses, the shock stalls, and at these high densities and temperatures, neutrinos are produced copiously. Because they are neutrinos, they're very weakly interacting, but because the densities are so high and the temperatures are so high, the mean free path in this context to neutrinos is very small. And so we have neutrino transport. We have a neutrino star in the center. And it turns out that those neutrinos, while they take away a lot of the energy of the event, also heat the outer material behind the shock. And in so doing, they can re-energize the explosion. And that's what we think. In addition, that heating behind the shock causes turbulent convection. It's like boiling water on a stove. You heat from below and you cause convection. The turbulence plus the neutrino heating seems together to be central to the explosion mechanism. The explosion is delayed, as I say, the shock wave stalls, but it's delayed, it seems, for only hundreds of milliseconds. That may seem like a very short time, but in this game, that can be hundreds of thousands of computational time steps. So what we also see is that the supernova seems to be a critical phenomenon. You go from a steady state eigenvalue problem of accretion to another steady state, which could be a wind solution, and the transition is actually the supernova itself. And it depends on some of the details of the neutrino matter interaction, convection. In the numerical simulations, it depends on resolution, but crucially, multi-D is important and necessary, it seems. It's also the case that with turbulence, you do get explosions most of the time. In the past, we were able to do many 1D simulations and maybe a few 2D simulations. Then we transitioned to the time when we could do many 2D simulations and maybe a few 3D simulations. And right now, what we can do is multiple 3D simulations per year. And that allows us to make mistakes along the way. And it makes it much easier to make progress so we can see the entire theoretical terrain. And that's what I hope to present to you now. The code we're using is called Fornax. It can go in 1D, 2D, and 3D. It's a multi-group radiation hydrodynamics code. It's not perfect, but it has lots of bells and whistles. For the cognoscenti who are interested in some of the details, it uses a two-moment transport equations with some closures. It is a Riemann-Goodenough method, and it uses that also for the transport. It has explicit hydro, but conserves energy and momentum to machine precision. It uses logically spherical coordinates, but it has a general metric covariant formulation. There's multiple gravity that is employed. It has a multi-group, of course. And importantly, because of the way we put the code together, we were able to speed the supernova simulations up by about a factor of 5 or 10 over previous codes. And this has enabled the multiple 3D simulations of which I was boasting. There are a lot of interesting neutrino matter physics questions. I'm not going to go into any detail here, although people can ask questions later about this. But there's inelastic scattering off electrons that deposit some energy. It's like Compton scattering. There's inelastic scattering off of nucleons. And these are harder problems to do numerically, but we've been able to incorporate at some level of precision these physical effects. We have approximate general relativity. This is not a fully general relativistic code. We wanted to get to the answers quickly. General relativity should be fully incorporated in the future. Most people are not doing it, and those that aren't really able to do much calculation. So this was our choice. We include gravitational redshifts, velocity-dependent terms in the transport, quite a number of bells and whistles. Now, this is a sample of a snapshot of one of the simulations that we've performed. That blue pseudosphere on the outside is the shock wave. In the interior, you can see the trajectories of representative matter particles, and they are not spherically distributed. This is the convection interior to the shock. You can see also those blue arrows coming in. That's the accretion in a non-rotating spherically symmetric progenitor model that, of course, is not spherically symmetric interior because of the generation of turbulence. This is also an example of the distribution in an explosion. That light veil on the outside is the shock wave, and in the interior is matter. It's colored by the composition, and the isosurfaces are entropy, just to give you an idea of the bubbles that really drive the explosion. And these are also examples. This is for a particular model of a 25 solar mass explosion. You can see the scale of 1,000 kilometers here. This is very early, about a half a second after the bounce at nuclear density in the simulation. The scale, though, is many thousands of kilometers, though it started out at 100 kilometers or so. And so that's an example. Now, I want to just talk about some of the important roles in the explosion, and one of those is the progenitor models. We inherit stellar evolution models from other groups, and then we map them into our code and follow them subsequently in ways they can't because they don't have the physics. This is an example of the density profile in some of those progenitors. This is from Suckbold et al. 2016, and this is the mass interior. This is the center at 0 and 2.5 solar masses, so it's an ersatz radius substitution, but it's the mass interior. And you can see for a 9 solar mass model or a 14 solar mass model or a 15 solar mass model, these profiles look similar, but they are different. This is the Chandrasekhar core in the center, and the outer regions are fairly different though. And these density profiles translate into different phenomena, different behaviors, and different degrees of explodability. In fact, these profiles make all the difference if you have everything else in order. So here's an example of how things have not really converged in the other realm of the progenitor evolutions. These are different groups at different times doing the evolution of the same 15 solar mass model. And the profiles, while they look a little bit similar in the center, and I'll call your attention to the fact this is 10 to the 10 grams per cubic centimeter, they look very different on the outside. And this translates into a different rate of accretion of material. This black curve, for example, will have a sudden decrease in the accretion. These curves here are flatter, and the accretion continues, and that translates into differences in the gravitational wave signatures, the neutrino signatures, the time of explosion, and in fact, whether it explodes. There is chaos, unfortunately, in the progenitor system. So these are models that were generated again by Suckbold et al. But 2018. And this is a 15 solar mass model from that group. And this is a 14.99 solar mass model. And this one does not explode, but this one does. And so there seems to be some non-monotonicity in these progenitors. And we really don't know what to believe. We do know, however, that the progenitors that are generated by these groups that we inherit do span much of the possibilities. And so that range can be studied, and we may not know the perfect mapping between the progenitor mass and the outcome, but we know the mapping between the progenitor range and the range of outcomes. And that is progress. I'll also call your attention to the following. In the Nagokura et al. Paper that we generated, we looked at the effective resolution. And you can see there are 3 different resolutions represented in this spherical grid. This is coarse, then medium, and then high resolution. And what we saw was the high resolution and the medium exploded, but the coarse or low resolution did not. And that shows that there is a numerical issue here. But fortunately, as you go to higher and higher resolution, it gets more and more explodable, and that's the direction you want. If it went the other way, we would be in trouble. But fortunately, that's not the case. And these are examples of the simulations. You can see the shock waves. Green is low entropy, then it becomes redder as it's heated by the neutrinos. That is zooming out. And you can see that 2 of the models explode, rotating them for artful purposes. But this one did not explode. And that is the low resolution one. You also see various interesting structures, large bubble structures, but you also see pinch structures, and I'll get into that a little bit later. I also want to call your attention to the following. Many of the simulations that were done in multi-D were first done in 2D, and 2D has an axisymmetry. And so you can compare 2 models, a 3D on the right-hand side versus a 2D on the left-hand side, and see some differences. Certainly you see the axisymmetry on the left-hand side, but you also see that on the left-hand side, there is a sloshing motion up and down. And the right-hand side, the same model does not do that in 3 dimensions. And that is a cautionary tale. For a decade, people were pointing to this sloshing up and down motion as a central feature. And it turns out that it's really an artifact mostly of the 2D simulations. What's not an artifact is the turbulence. That is real, and that is driven mostly by neutrinos. This is neutrino-driven convection. And when the neutrinos are dominating, neutrino-driven convection dominates the turbulent generation. So that's one thing to notice. It's an important one as well. And so now I want to get to some of our new 3D simulations, and much of the center of the talk is going to focus on that. And I will start by saying that almost all our models explode. They explode without putting anything in there to make them explode. We take progenitor models, we put them in the code, we run it, and then we see what is represented here is the average shock radius. This is 100 kilometers, 200 kilometers, 300 kilometers versus time after bounce. So it collapses on the left-hand side and then gets to 0, bounces, a shock wave is formed, and this shock frequently just starts to go out. It stalls, but then starts to expand, and that's an explosion. A few of the models do not explode, and I can try to explain exactly why those do and those others don't. And some of it is subtle. And not everything is resolved. So maybe there'll be some circumstances under which these would explode as well. If there's a lot of turbulence in the progenitor, for example, or a bit of rotation. And these models are non-rotating. Nature has rotating objects, and I can talk about that at the question period. But you can see that the majority of the models explode, and these are 3D models. This is an example movie of the simulation of a 16 solar mass model that explodes. The colors, again, are entropy, and that's generated by the progressive heating by the neutrinos. Red is it's getting hotter and hotter. That white dot in the center is the neutron star that was newly birthed. And you see the bubbles. It has a dipolar structure in this particular calculation, but it also has this pinched region. And if you look at the velocity vectors, there's actually accretion happening along the waist here as it's exploding. That accretion contributes to the neutrino luminosities because you have accretion power as a component of the neutrino emission. And so in multi-D, you can get simultaneous explosion and accretion. And if you can continue with the accretion, you can continue the neutrino emissions at a high level, which are important for the explosion. So the breaking of symmetry, the breaking of spherical symmetry that allows this simultaneous accretion and explosion may be central to the explosion of many of these models because it enables the continuous powering during the explosion, which if it were in spherical symmetry would turn off that power because it turns off accretion. An explosion is just the opposite. This is the same model, but with the composition. And I just want you to call your attention to a few points here. This is the electron fraction colored, and you can see the purple and blue and red are different electron fractions, and I'll call your attention to that. And the electron fraction is directly connected to the nucleosynthesis. Red is a higher electron fraction above 0.5, where 0.5 is symmetric material, like carbon-12, oxygen-16. This will be nickel-56. And the purple is low electron fractions. And so you see a distribution, let's see, you see distributions that are very, very aspherical in the element distributions as well. And that's what you seem to see, although not perfectly, in Cassiopeia, for example, I mentioned in the beginning of the talk, but in many supernova remnants. This is just a still of that same model hydrodynamically in entropy, and you see that waste in the middle where there is still accretion. It's going to stop, but at that phase, at around 2/3 of a second, it's still accreting, while it's still exploding in another direction. Something that you can do only in 3 dimensions, when you break symmetry. And here's the element distributions where you have purple, blue, and red being different compositions that are giving you different elements. And that white dot at the center is, again, the neutron star that was left behind. So this is just a montage or collection of some of the exploding models. Again, green is when it's just starting out, and red is when it gets hot enough and starts to explode. And we're zooming out a bit again, just to give you a sense of some of the morphologies and shapes. But the one at the center doesn't explode. But look at what it does do. I'll have to show that in another slide. But what it does do is it starts to slosh and have an m=1 spiral arm that is created. And almost all the time we see a unsuccessful explosion, leaving behind a compact shock that doesn't get re-energized, we see this this spiral mode, this sloshing mode, and that has a direct signature in gravitational waves. This is just a simulation from a distance without any zooming to give you an idea of how it develops. This is starting out at 1,000 kilometers or so. It's going to end up at about 10,000 kilometers, which is still small, but it's this has evolved over 1 million numerical time steps, a little bit more than that. And you can see the basic structures, again, fairly uniform, where the colors give you a composition metric, and the light blue veil is the shock wave, and you see the bubbles inside, which reflect the bubbles that drive the explosion. And this is a similar thing, but it's a 25 solar mass model showing some of the trajectories of the matter. The matter falls in, and then it gets caught up in the turbulence behind the shock. You can see the bubbles that are created as well. You can also see the basic scales changing. That went from 350 kilometers now to 500 kilometers. This is going to zoom out again. And so you see, as you have accretion, you have the shock wave moving out to meet that accreting material, but in fairly complicated structures that are generic. And they're generically in bubble form because of the nature of the neutrino-driven turbulence that's driving the bubbles. This is the same simulation, but we're looking on the inside, just at the inside material, and zooming out and following all that turbulence. And you can see what individual trajectories do as we zoom out and the shock wave moves out. Each one of those lines is a parcel of matter that's being ejected. And you can see the general character of the distribution and the distribution of the blobs or the bubbles with that waste that is pinched where there's still continuing accretion. And because I like these so much, I'm going to show you another one. This is the higher resolution calculation for a 19 solar mass model. They all do something similar, but I want to call your attention to the following. Here we're going to focus on the center. And you start to see in the center that there is rotational motion that is induced. That color changes because the camera moved inside the shock wave. So you can see some of the trajectories that are now swirling around. And this is induced rotation of the outer part of the protoneutron star that wasn't rotating initially. What's ejected has the negative angular momentum. And so you can actually spin up the neutron star that started out not spinning without any angular momentum because of the material that falls back and falls back on either one side or another. For one reason or another, I just like this movie, so I'm going to include this. This is just a still showing again what the trajectories look like in this tangled web interior to the shock wave just before explosion. This is just in the early 150 milliseconds after bounce. There's the shock wave, and it's about to be re-energized completely and become a supernova. What's left behind in the protoneutron star is represented by this. In fact, I'll show a couple of pictures of this, where the isosurface you're seeing is a constant density surface. It's not quite a sphere, and that's the neutron star at birth. And around it is material swirling around still. Material has been accreted. Some of the material that was on the surface of the protoneutron star is being lifted off. And so there's a lot of complicated dynamical motion in these early phases. This is actually a little bit later, and you notice that it shrunk. This is larger, this is smaller, but there's still this tangled web on the outside. And this is a sequence just before explosion, where you see at the top a large protoneutron star, and it shrinks during this time, and it shrinks because it's losing electrons and electron neutrinos, and it's losing heat and energy. And so it's in a Kelvin-Helmholtz phase, compressing to a much smaller configuration. For example, this radius here is about 50 kilometers here in radius, and it goes down to about 30 kilometers, 25 kilometers here, and will continue to shrink. And so this is the evolution, the early evolution of the star that is the protoneutron star, which is the birth of the neutron star itself. And again, here's a sequence of these sorts of things where the inner region surfaces are isodensity surfaces. And you can see as they evolve from left to right, middle, left to right, bottom, left to right, the tangled web around them is preserved, but evolves, and the object shrinks. This is also focusing on that interior, the same model, in fact. And you can see in time how this inner region has evolved. This is actually slowed down because of the connection speeds, but that's okay. See if I can, there we go. So I want to show some of the results of the observables. And one of the observables is the neutron star mass left behind. Each one of these is a different progenitor, where the 2D models are given as thin lines and the 3D models are given as thick lines. And what you see is, as a function of the progenitor mass, let's say this red line is a 19 solar mass, is the neutron star mass that is left behind in the explosion. And this is the baryon mass. You have to correct for the binding energy, and that's going to be about 1/10 to 3/10 of a solar mass, depending on the actual mass. So you correct this down. And this gives you masses that are in the range of the masses of neutron stars that are observed. Generally, those that are observed are going to be weighted by the mass function, which weights the lower mass massive stars. And so you can just read off what masses we would predict here. And some would be fairly high. This is the radius of the protoneutron star that I was referring to with those 3D plots, but this is just the average radius. And you see in a time of about 700 milliseconds after bounce, the radius is shrunk by a factor of 2 or more, and will continue to shrink over a long period of time of many seconds. This is the same sort of thing with the a longer set of simulations in 2 dimensions here, because it's much cheaper to do 2D simulations. And you see that the neutron star mass, the baryon mass, is flattening out. And you can see the range that we get for a much larger range of progenitor masses, from 9, which will leave behind a lower mass massive star, neutron star, to 26 or so, or the 20s solar mass range, which will leave behind a higher mass. And if you correct this for the gravitational binding, this is going to be something like 1.7 solar masses. And so this is the range of predictions we get. Importantly, we also get the following. When you simulate for a long period of time, you finally get asymptotically the final energies. For the lowest mass progenitors, like the 9 solar mass progenitor, the energy of the explosion is determined within the first second or so. And so you don't have to simulate as long as you do for the more massive ones, which really require simulations that last for many, many seconds to achieve the energies of the supernova that we know and love. So here's the explosion energies in betas, which are 10 to the 51 ergs. And you see that in the early phases, the energies are actually negative, even though they're exploding, because they haven't really overcome the full gravity. The shock waves are moving out, but it takes a while for the energy that's being deposited by neutrinos to overcome all the binding and for this number to become positive. And you see that for the more massive ones, you really have to wait a long time. 5 seconds or so is necessary to see the asymptotic explosion energy. But when you do, you see energies that are in the canonical supernova range, from about 1/10 of a beta to a few beta. And this is just by the neutrino mechanism. This doesn't mean that magnetic fields can't play a role sometimes. This doesn't mean that a magnetar can't, at the later stages, drive some of the light curve or even some of the explosion. But generically, without much rotation, we easily get explosion energies that are in the observable range, in the observed range, but only after long simulations. And these long simulations were required in order to see what the asymptotic state was, and weren't accessible until recently. This is a very expensive set of calculations. And these are comparisons. These black dots are those energies of explosion, and the crosses are some measurements or inferred explosion energies versus ejecta masses. And so you can see that we get more or less, for the lower ejecta masses, we get lower energies, and higher ejecta masses higher, with a fair amount of chaos or stochasticity. And this does follow crudely the trends that are observed, although I suspect that there's more to learn here. But there is chaos in the results. And that chaos is a natural consequence of the turbulence that is generic physically in these objects. So a given models, like the 15 solar mass model at a given metallicity without rotation, will give as an end product neutron star masses that are slightly different and energies of explosion which may be fairly different just because of the chaos. And that's an interesting aspect that hasn't been completely worked out. The ejecta composition, though, is also very interesting. If you histogram the mass distribution in the electron fraction to which I referred, where normal matter is about 0.5, although hydrogen is 1, but just about everything else is near 0.5, you get a distribution which is fairly proton rich, but most of it is at 0.5. And note that this is a log scale. So we get most of the material that is more or less symmetric matter, but a fair amount of proton rich material. This is not our process material, but it could be the RP process. It could produce some very exotic, but very interesting observed element isotopes. It also, we could produce some neutron-rich material, but by and large, many of the models show some proton-rich material at a part in 10 to the 3, a part in 10 to the 2 of 100%, which is mostly symmetric matter. Now, the protoneutron star left behind is doing some exotic things. And this is a set of postage stamps showing some of those exotic things. This is radius versus time, and this is colored by the, I think in this case, it's the RMS radial velocity in the inner region. The outer region, this is 50 kilometers. The explosion is off the scale. It's not here. The protoneutron star is in the center. And you notice that you start getting interesting velocities in this band here. There is convection going on in there. That's protoneutron star convection that lasts for a number of seconds. It's different for each progenitor. And this vigorous convection may be one of the sites for the generation of pulsar magnetic fields by the dynamo action, which is, I will not go into in detail here, but I will note that it's generic, and the redder the color, the more vigorous. And so it gets more vigorous with a larger mass progenitor, with a larger mass left behind for the neutron star. This is showing that inner region, and is just showing velocity vectors on a given surface. This is an isodensity surface, and it just shows some of the motion that is achieved inside this turbulent inner region. This is just like a convective region in a star that is bounded by radiative regions. And it's one of the first simulations in 3 dimensions of a star that has a radiative zone, a convective zone, a radiative zone, etc., in an exotic context, to be sure, with the full radiative transfer as well. So I emphasize this and provide it for your delectation. Let it go once more. You can see those arrows at the top that shows an artifact of the axis in 3D. It's not perfect because it's hard to do the axis properly. It doesn't really interfere too much, but it's there. And this is the hydrodynamic flux in that region. So this is just the flux of kinetic energy plus the flux of thermal energy, etc., that you would calculate in a convective zone when you don't have to use mixing length theory. This is actually calculating it on average, angle averaged, for these objects, a whole range of objects. And you can see the power associated with that flux, and we've converted to power by multiplying by 4 pi r squared, is something like 2 times 10 to the 52 ergs per second. So it's quite significant. This outer material here is just flowing in, that's accreting, and the rest of it in the exterior is actually exploding. So this convection is happening during the explosion. I'll show this once again. I'll also call your attention to the fact that some of the very massive objects explode as supernovae. The evolutionary models have given us structures that do explode, even though they're 60 solar masses. However, I think that most of the most massive ones probably don't explode as supernova in the classical sense, and many of them will leave behind black holes. What we do see is the majority of those objects from 8 to 25 solar masses do explode according to our simulations. Okay, I'm going to skip this. So neutrinos, as I say, are central to this. And neutrinos were detected from supernova 1987A. We saw 11 neutrinos in Kamioka 2 and 8 neutrinos in the IMB detector under Lake Erie, one of the Great Lakes in North America. But that wasn't many. With the new detectors, some of which are listed at the bottom here, we'll be able to see thousands of events from a galactic supernova, a core collapse. And so I want to summarize some of what we expect to see. This is just some postage stamps of some of these detectors. Dune Detector is being developed by the Department of Energy in the US to do mostly neutrino oscillation experiments, but it will be a superb detector of electron neutrinos of 40 kilotons. The Juno detector is being constructed by the Chinese in the southeastern China, not far from Hong Kong. Super Kamiokanda, of course, is a storied detector. This is when the water has been partially drained and you have some of the maintenance workers looking at the phototubes. And this is IceCube, which has the most mass, but doesn't have any energy resolution of significance, but will be able to see supernova neutrinos because it will affect the background in IceCube. We know the cross sections for the interactions. These are just examples. And what we expect to happen is the following. After bounce, the shock wave moves out, and that shock wave is born in an optically thick region, but then it quickly goes to an optically thin region. When I say optical, I mean neutrino optical depth. And what you get is a burst of electron neutrinos, in theory, that can be 3 times 10 to the 53, 4 times 10 to the 53 ergs per second over a period of about 10 milliseconds. This is a generic prediction of all models. What you also see is the anti-electron neutrinos here in green and the mu, tau, anti-mu, and anti-tau neutrinos all bundled together here in black that rise. And it's all 3 of these groups where there are 4 species here, anti-electron neutrinos here, electron neutrinos here, and anti-electron neutrinos here in green that dominate the losses, and over periods of tens of seconds will take away the binding energy. These are examples of the luminosities you get in the first 700 milliseconds for the different progenitors. And the major thing I want to call your attention to, these are different species, electron type, anti-electron type, and the mu's, taus, anti-mu's, and anti-taus, is that there is after the breakout burst, which is this first burst here, there's a plateau, and that plateau is higher for higher mass progenitors. When we looked at those density profiles, some of those density profiles were shallow, some were very steep. The steep ones have less accretion, and so the luminosity is fairly low in this context. So that might be a red curve from the 9 solar mass. The 25 is the purple, and it has a luminosity peak that is 2 times that. And so this is a prediction of the theory. The accretion context will determine the neutrino emissions. When they explode, the accretion, some of the accretion stops, and what you get is a reversal, of course, some continued accretion, but at that explosion time, you can see a decrease in the neutrino luminosities. So this blue curve decreases, this light blue curve decreases, this purple curve decreases, etc. That is a signature of explosion. The average energies are also predictable. I'm not going to go into that, but it's on the order of 15 to 20 MeV. And those can be detected in the detectors I mentioned. It is also the case, and this has never before really been calculated well, that the neutrinos are not emitted spherically. They're emitted almost spherically, but there could be a 10 or 15% asymmetry in the neutrino emissions because of the asymmetry in the accretion, the asymmetry in the evolution of the protoneutron star, a number of interesting effects, not all of which I'm going to go into without unless there are questions. But you see that the asymmetry, which is here's the fractional asymmetry, evolves with time. and can be, for many of these models, 5 to 15%. And so when you detect the neutrinos from a given event, you're detecting one direction, and in another direction, the emission is going to vary, of course. And we've quantified that here for the first time. This gives you an idea of the same thing, where the color represents the excess. Red is an excess of luminosity in a direction, and blue is a deficit. And to emphasize it, we actually make the radius of the thing similar to the color. So blue is indented and red is bulging out. And this just shows, as the neutrino luminosity evolves, this is the integral over time, how the angular distribution changes. It's still only 5 to 10% in this model, but it's a real effect. The actual detailed magnitudes will depend on much more detailed neutrino transfer, but this is a pretty good guess. Not only are neutrinos going to be emitted and observed and seen copiously, there are going to be thousands, as I say, events in many detectors if we're lucky enough that they're online during a galactic core collapse. There's also gravitational radiation. And gravitational radiation is sourced by the time-changing mass quadrupole moment of the object. There are many components here, and I don't want to go into much detail here. But for those who might have questions, I will get back to this. But I will show the following. On the right-hand side is the gravitational wave strain in one particular polarization versus time. On the left-hand side is the corresponding hydrodynamic development. You can see 200 kilometer, there's the shock wave, there's turbulence in there. And this is a 2D simulation that was done more than 10 years ago. When you get an explosion, that explosion is frequently asymmetrical top and bottom. When it's asymmetrical, you get not only the gravitational waves, but you get a gravitational wave signature that doesn't cancel out on average in time. This is memory for those who know something about gravitational waves, but it's due to the asymmetry in the explosion. When there's an asymmetrical explosion, you get these non-zero average strains, which are characteristic of these asymmetries. This is not something that is easily seen in LIGO. It's certainly not seen in merging neutron stars to any great degree, although there is some component there. But this is also a generic feature of an asymmetrical explosion. This is just a collection of some 3D models where this is a 9 solar mass at the top and a 60 solar mass at the bottom, 25, and you get certain generic features. These are non-rotating models. The non-rotating models have an early convective overturn phase, and then there's a delay, a slight delay, until you get much more vigorous gravitational wave strains. And this is when the turbulence is really developed. So this measure here, this region here that develops from the early stages, low to high, is the region where there is significant turbulence. And this is a prediction of the theory. There will be a lull, and that lull will depend on the time it takes to get to full nonlinear turbulence. On the right-hand side of the corresponding spectra. And if you see the scale down here is 1,000 hertz and 100 hertz. This is the advanced LIGO sensitivity curve, and this is the Einstein telescope sensitivity curve. And you can see for 10 kiloparsec distance, which is further than the galactic center, but it's still in our galaxy, for two different models, where the power lies. And the power lies mostly at the hundreds of hertz to kilohertz range. And that is detectable, although the very high frequencies are going to be hard for LIGO, but are possible depending on the distances and details. But you can see that at 10 kiloparsecs, the signals are stronger than are necessary to be captured by advanced LIGO in principle. And this is where the power lies. Let's see, these are also some models I won't go into in detail. If you do a spectrogram of frequency versus time, and you color it with the amplitude, you see a band in here. This is for a 25 solar mass 3D model. This band is due to the astroseismological excitation of a fundamental mode of oscillation of the protoneutron star. You're seeing neutron star seismology. This is the F mode. There are G modes, P modes. This is the F mode between the G modes and the P modes. And it grows at a rate determined by that shrinking of the neutron star. And this is over just 600 milliseconds. And that's where most of the power is. There's some power at lower frequencies, etc., but not much. The dominant power is basically this F mode. And that F mode is generated by that accreta, those plumes that are coming and hitting the surface and causing the bell to ring, that inner region to ring. And we see this for a lot of models, this F mode. There's a low frequency component, so-called standing accretion shock instability, which doesn't really factor very often. And for non-exploding models, you see. For exploding models, you rarely see it. But the F mode is always there. We can see what the correlations are between the turbulent energy above the protoneutron star and the energy and gravitational waves. And it's approximately a square, or 1.88 we had, power dependence. Here's the 9 solar mass, and here's a range here. It fits nicely on a log-log plot, and it verifies the basic mechanism, which is these plumes. If you look at the frequency normalized to the mass of the protoneutron star and the radius of the protoneutron star cube versus time, for all these models, they don't vary by more than about 10 or 15%, this combination. And so if you could measure this frequency and measure a few other things, you'd be able to get the mass and the radius of the object, and probably versus time. This emphasizes the same thing, where this particular curve is actually the energy radiated normalized to certain units versus time for the different models. And there's a variation of about 15% when normalized. And so this is the frequency, that F mode frequency. And you can see there's almost a one-to-one correspondence between the evolution of this frequency and the emission of the energy. And so there is a lot that could be learned about what's happening in real time from the gravitational waves and from the neutrinos and from the two analyzed together. We can look at the equation of state dependence, the nuclear equation of state dependence of this F mode frequency and the behavior. And you can see 3 different common equations of state that are used, and the different evolutions. That's going to be hard to distinguish, but in principle, it is distinguishable if we're very, very lucky. Now, I haven't included rotation until now, and so I will. And in gravitational waves, the rotation introduces a time-changing quadrupole moment because it introduces an oblate object. The object is oblate and it's collapsing, so you get gravitational waves from the very beginning, and it bounce. You get this oscillating oblate spheroid that gives you lots of gravitational waves. At later times, this F mode starts to dominate. The rotation does affect some of those details. And here's some of this signature. Without rotation, you get a little bit of a blip, then the rise to the turbulence and the F mode domination. The frequencies can be discerned, but this is really rather stochastic in amplitude. With rotation, you get this big early emission that's characteristic. And you could sonify this. You can convert these frequencies into sound, and I'll do that in a second. But I want to show, as a function of rotation, that as the rotation rate increases, this early phase signal gets larger. It also affects the late phase stuff. And so there's a correlation between those, which is useful. But I don't want to go into that right now. But this is sonifying it. Can people hear this? I'll do that again.
Yes, we can.
Thank you. Okay, listen. And listen to this. You see that? Listen to that first chirp. That first chirp was rotation. Now, I'll do it once more. And notice again, you look at these things and it looks like it's all a mess. But when you listen to it, you see the frequency in every single case always goes up. That's a signature. These are some more models. They all do the same. The energy that's radiated in gravitational waves can be given here. And it's not a lot, but it doesn't need to be. But you have to simulate for a long time to see that it's about 10 to the minus 8 solar masses equivalent. Many people had simulated for just the first 100 or 200 milliseconds, and they therefore missed most of the important phase. But it is a function of progenitor, etc. The lowest mass ones have the lowest signals and they saturate early, but the more massive ones last for a long time and are 100 times the energy. And so that's fairly useful. This is a movie similar to the neutrino anisotropy movie, but giving you the gravitational wave anisotropy. And it's more than that. When the neutrinos are emitted, they're emitted anisotropically. They have a lot of mass energy. And so the time-changing quadrupole moment of the emitted neutrinos is also a signal. It's just very low frequency. But this gives you the angular distribution of the gravitational wave signature of the neutrino emissions, which is added to that from the matter. And so what we have are detectable characteristics in explosion energy, neutron star mass, gravitational waves, neutrino emissions from state-of-the-art 3D simulations that can be used to predict and to inform the observational campaigns of the future. What's shown here is, again, representative gravitational wave spectra versus the sensitivity curves of advanced LIGO, and then the Einstein telescope and the Cosmic Explorer that are being suggested for the 3G incarnation of gravitational wave astronomy. And you can see that in principle, all these things are detectable. So I think that in fact that theory and observations and experiment are starting to converge with the numerical arts to actually inform in some detail what these objects are doing to provide signatures of the event, the very dynamical event that launches the explosion that is the supernova explosion. And I can summarize the basic results here, but I think I'll stop here and leave it to questions. Thank you very much for your attention.
Okay, thank you. Thank you very much for this talk, fascinating talk with a lot of fascinating topics. And I will start with a question just to break the ice, if it's okay to everyone. Sure. Well, I know that the neutrinos play a very important role here, and I would like to ask you a little bit about the mechanism, the physical mechanisms behind the neutrino, the turbulence driven by neutrino. How is this turbulence formed? What are the interactions involved?
Certainly. The neutrino, there's a neutrino sphere, just like a photosphere of the sun. And that is around, say, 50-kilometer radius. When the shock stalls at maybe 150 kilometers. So there's a region between the neutrino sphere, which radiates again, almost like a thermal black body, neutrinos, and the shock wave. Behind the shock wave, there are liberated neutrons and protons. And so you have electron neutrinos that are emerging, and they'll be absorbed on the neutrons. You have anti-electron neutrinos that are emerging, they'll be absorbed on the protons. In the super allowed charge current reaction that has been measured and is well known, has been calculated in some detail, and so is not only generic, but is unambiguously an important factor here. There are other processes as well. And so some of those neutrinos that are being emitted will deposit as they get out energy, and maybe only 10%, maybe only 5%, but enough so that you heat the material between the shock and that neutrino sphere. When you heat material like that, most of the heating happens in the lower regions. And if you're heating from below, you're making bubbles. You're causing material to have a little bit higher entropy there. There's a little lower entropy on the outside. And when you have a negative entropy gradient, you can have overturn. And so that is the origin of turbulence and convection in these objects. It's heating from below by neutrino heating. That neutrino heating also is energy deposition, so it also contributes to energizing the explosion itself fundamentally. And then after the explosion starts, it will continue to heat the material and is essential to making sure that the energy at infinity is positive. I hope that helps.
Yes, it does. Although I have to do a lot of thinking about it, but thank you.
Because it's very unusual. It's something like you really never face in other situations. So
Exactly.
it has a very solid physical basis, but nevertheless, the context is difficult. It's not easy.
Okay, we have another question from Reynaldo.
I think I bet is
sorry.
asked before.
Sorry, I'm sorry.
Hi, Adam. Here is Elizabeth Dalpino speaking. How are you doing?
It's good to hear your voice.
Amazing talk. Thanks a lot. So I have a couple, if I may, I have a couple of questions. One regards magnetic fields, the presence of magnetic fields, because we have lots of effects, ingredients like convection, rotation, and the magnetic field of the remnant itself, of the progenitor itself. So we might expect dynamo amplification, as you mentioned, and this may introduce dynamical effects like changing a little bit the convection evolution itself, and also the symmetry of the explosion, right? So can you comment on these effects? Because as a matter of fact, we have the magnetars as well, and this recent event that occurred in NGC 253 starburst galaxy. So can you comment on these effects?
Yes. You're absolutely right. And these turbulent conditions in the protoneutron star deep inside, and turbulent conditions behind the shock, which are now being shown, there's no way that won't affect the magnetic fields. The old story was that you have magnetic fields that are generated in the progenitor, and that those magnetic fields are flux frozen from the white dwarf-like configuration to the neutron star configuration, and that could give you fields that are sufficiently large to explain pulsar fields, about 10 to the 12 Gauss.
Exactly.
That is the old story, and that can't possibly be true because of this turbulence. You start out with those initial fields, and this turbulence is going to completely change things. It'll change the multipolarity structures. There are many contexts in here where you can have dynamo action. There's going to be some rotation and differential rotation. This is a perfect environment for the generation of field. What we don't know is how we can explain the spectrum of fields that are observed, from very low fields, which are probably started out as regular pulsar fields and were affected by accretion at much later times. But from, let's say, 10 to the 12 Gauss to 10 to the 15 Gauss, we don't know what types of progenitor systems would give the high fields asymptotically and what would give the lower fields, even though they're still very high. And that's a subject of current research, but there is no way that the magnetic fields of pulsars and magnetars aren't going to be fundamentally affected and probably created during this few seconds of evolution. We haven't figured this out, though. My own feeling is that we don't know. My own feeling is it's very possible that with significant rotation, you cannot suppress significant dynamo action. If there's very rapid rotation, I would expect, in fact, that very large fields would produce dynamically, and those fields would actually have an effect on the mechanism with the neutrinos and may actually dominate the neutrinos. You can't get rid of the neutrinos, but the mechanism, the magnetic fields could in principle give you jets, and those jets could power the explosion. And those explosions may be even more energetic than the generic neutrino explosions, which would be on the order of 10 to the 51 ergs. You might be able to get to 10 to the 52 ergs with a magnetically driven explosion with rapid rotation, where the rapid rotation might have in the rotational component enough energy to, via the intermediary of magnetic fields generate very energetic explosions. My only point is, in this context, really rapid rotation doesn't seem to be generic. That if you look at pulsars and you do a little bit of theory, although there's some caveats here, most pulsars seem to be born rotating slowly. And if you need rapid rotation to get to high fields by dynamo action, then that may not happen very often, but it might happen in the so-called hypernova case. Hypernovae seem to have energies that are on the order of 10 to the 52 ergs. Those are associated with type 1c broad line supernovae, some of which seem to be associated with gamma ray bursts. Right. So I would think that less than 1% may have rapidly enough rotating cores that you can get a bipolar magnetic driven explosion, leaving behind magnetic fields that are easily 10 to the 15 Gauss. But I don't know what the generic case would be. But I do agree with you. This is an important topic. And there's many places in this context where magnetic fields can be generated by dynamo action. I just don't know what the final state is. The multipolarity structure, the degree to which you have a dipole as opposed to a higher multipoles is also not clear. That may require rapid rotation or some sort of rotation. So this is a good set of questions. I have no good answers, but I will say that this is an active area of research.
Do you have plans to include the magnetic fields in your simulations? Because I know it's challenging, expensive, but you know, you have all the ingredients there.
It's not expensive. The neutrinos are the most expensive part.
Yes, this is what I mean. You have all the ingredients there already, but magnetic fields.
No, we're going to do that. In fact, I had an old code that wasn't the Fornax code, which is the Vulcan code, where we did include magnetic fields. We did 2.5D simulations where we included the phi component, but the derivative of the magnetic field in the phi direction was set equal to 0. But we did have 3 dimensions of the magnetic field with the neutrinos, etc. And we got these bipolar jets. Right. And so it's possible that was with rapid rotation. It's possible, and we actually underestimated the degree of magnetic field amplification. So I think those rapidly rotating contexts give you these bipolar jets a fraction of the time, maybe not generically, and that is an important key component in the broad story.
Right.
Also in the case I'm sorry, go on.
Any evidence of the Taylor effect for magnetic field amplification in these stages with your MAGD version? I know that it was 2.5, and 2.5 is not enough to see the real dynamo amplification, but
that's right. So we had linear amplification, and that itself was enough, depending on the initial fields. But we could also estimate the rate with which the dynamo would operate, the time scale, and it was less than 10, 20 milliseconds.
Right.
So it's an environment which would love to be to generate field in many places. The protoneutron star, convection itself deep in the interior of the object left behind, as well as the material interior to the shock wave. What we don't know is exactly what the final state is, but we are going to put magnetic fields into Fornax.
Yeah,
it will be about a 10% hit, but not a big hit in time.
Right.
And we have done some preliminary calculations, and we are looking at the generation of field. I will say that there is almost no way, given the power densities in these contexts, that you don't generate large fields generically. The question is whether you generate large dipole fields.
Right.
And those are what's observed.
Great. Thanks a lot, Adam.
Sure.
Okay, so let's move on with Reinaldo. Your question?
Hi, Adam. Thanks for the talk. I have 2 short questions. One is there time during the characteristic time for the evolution of this shock, the formation of the turbulence and the evolution of this shock, for these chaotic motions to become a turbulence completely fully developed? And my second question is, it seems for the results you showed us that turbulence has a very crucial role in the evolution of the system, and there are some problems for the numerical convergence. Do you think that it's possible analyzing maybe the evolution of the power in the spherical harmonics, or the power spectrum, try to model the small scales, to model the subgrid scales phenomena?
Well, we haven't been modeling the subgrid phenomena. That would be very useful, and I think that that is a worthy line of investigation. We have done the decomposition of the turbulence field in modes, and we've looked at the spectrum, and we've estimated the degree of numerical dissipation, and that was done in the resolution study, the Nagakura et al. Paper in 2019, I believe. And so I'll refer you to that. There is enough time for fully developed turbulence. The characteristic overturn times are really only a few milliseconds to 10 milliseconds. And so, and we're simulating for many times that. So I don't worry that we hit full nonlinear saturation. Numerically limited, physically over these same periods of time, the nature is certainly saturating, and you have fully developed turbulence before the explosions.
Thanks.
Almost all the time. Now, I should emphasize, and this is an opportunity to do so, the turbulence has a stress in it. There's turbulent stress due to there's a turbulent pressure. That turbulent pressure is one of the central reasons turbulence is important. It's adding that extra turbulent pressure in with the regular gas pressure that puts it over the top. The turbulent pressure, when you look at it, it's actually anisotropic. And so the pressure tensor actually is more in the radial direction than in the sideways directions. That helps with the explosion. And it's also the case that when you analyze the turbulence, you can make the analogy with a gas in the connection between the energy density and the pressure associated. For a gas, you have a certain gamma, and the gamma of the gas is 4/3. The effective gamma of the turbulence is 2. And so for a given amount of energy or energy density, you're more efficient at producing pressure if you make it turbulent. And that's one of the other positive things.
Thanks.
Any other questions?
We have one question.
Yes. Thank you for the very nice talk. Can you hear me?
Yes.
Regarding with the neutrino mass, can you accurately constrain the neutrino mass from your models when comparing with actual neutrino events?
Well, that's a good point, and I swept that under the rug. What we predict are the non-oscillating neutrinos, and then we can oscillate them by adiabatic processes or whatever processes there are. But we've modeled it with the adiabatic transformations, so that in the detector we see the mapping between the initial neutrino signal and the signal that the detector sees. And so that does have a significant effect of transformation of electron types into mu types, etc. And each of those detectors is sensitive to a certain flavor of neutrinos because of those cross sections. So we need to know that transformation. That transformation, if it's adiabatic, doesn't depend too much on the mass. And the masses are likely to be low enough that the delay due to the light travel time, or the differential neutrino travel time for different energy neutrinos, is too small to be noticed. So I don't think we're going to have a good handle on the masses. We may have a handle on the mass hierarchy to know whether it's an inverted hierarchy or a normal hierarchy, because those predict different signals in the detectors for the same emission. And there are some diagnostics. One of the best is that breakout burst. The first breakout burst that was at 4 × 10⁵ for 53 ergs a second in electron neutrinos wouldn't be electron neutrinos in the detector. It would be some sort of mix. And for the normal hierarchy, that burst is almost completely suppressed. For the inverted hierarchy, it's not completely suppressed. You should see a good fraction of it. And so that's something as well. But there are other signatures as well. But to see the mass directly, the mass effects directly might be difficult.
Well, thank you.
My pleasure.
Okay, I think that was the turn of Professor Antonio Mario. I think was after Juan.
Yeah, thanks. Well, thanks for your talk. Appreciate it. I'm not a theory person, but I would ask you one question. Early in your talk, you were showing a model that developed sort of dipolar structure. Is that so? What again was the reason for breaking the spherical symmetry? Was that rotation?
Well, no, it wasn't.
And a related part.
It found its own direction. Fortunately, it wasn't along the axis. That would have been annoying. But these models just explode in whatever direction. That's due to chaos. The direction they go in without rotation.
Because I remember you were not talking about rotation back then, so I was curious. Okay.
Yeah. So it breaks the symmetry. It's just like any symmetry breaking, and it turns out an explosion is basically a monopolar instability. You explode in all directions to 0th order. So that you could do a modal analysis of the shock and see if the shock is unstable to perturbations. And so you could look at the monopole, the dipole, the quadrupole, all these sorts of things. And when you do that, you find out that the monopole becomes unstable at the same time the dipole becomes unstable. So those lower order L's seem to go unstable first. And one of the things that happens is that you get a bulge in one direction as the shock oscillates around a bit. You get a bulge in one direction, and it will continue out. It'll be unstable, pushing out in that direction. And then it pushes out in all directions, but it started out in one direction. And so you naturally get an L=1 instability at about the same time as the L=0 instability, but there are others as well, and it's really nonlinear, and you can't really do that, but that's sort of what we got. We put an analytic model of that together in 2003, and it seems to hold more often than not, but it's a mess.
So does that get carried down up to the surface? Is that because I wasn't clear where the skills were?
Partially. That's a complicated question. What you get in the first seconds is a complicated distribution that has bipolar, monopolar, quadrupolar structures, and L=5, and all these sorts of things. There's a decomposition. But as that shock wave moves out through the star, it encounters interfaces in the star between the helium and hydrogen, the helium and carbon and oxygen. There are reverse shocks that go through it. There are a number of things that modify that initial structure. But the basic dipolar anisotropy survives all those transformations, so that a lot of the structure is suppressed, etc. But the basic lowest order anisotropies seem to survive even after all these transformations due to the propagation of the blast through the star and the subsequent production of the supernova remnant. So this dipolar structure that you see here just emerged in that direction and continued, was driven by the neutrinos. It liked what it saw. And at the same time, there was accretion along the transverse directions that emphasized this bilobate, two-lobe, two-structure explosion.
Okay.
There's a lot to say, and there's a lot that isn't. There's a lot that's generic. There's a lot that isn't generic. So it's hard to answer in detail because this is a very chaotic, complicated context.
Yeah, I guess in the end, I guess I was after observational clues to that to that breaking.
Absolutely, and there will be the element distributions, the basic large scale structure, not small scale, it's a large scale structure,
right?
To be preserved. But there's going to be transformations that are going to make it a little bit more difficult to see the explosion in the supernova remnant. But you will be able to do it. It's just going to be transformations, and there's going to be some residual effect that will survive. And we're starting to see that in the element distributions and in the lobate structures, the bubble structures, but they're not exactly what we started out with.
Right. Yeah. Yeah. Of course, you have Thomson scattering there. I mean, way up in the envelope. So you have Thomson scattering. So if you have that plus the some asymmetry, right? There will be observational effects to that. That's right. That's maybe. Thank you.
My pleasure.
Okay, let's move on with Germán. Would you like to ask your question?
Yes, thanks for this talk. I have a lot of questions, but let me ask only two. One of them is about if you are able to produce in your simulations very low mass proton-neutron stars, things like half the solar mass or something like this, in order to, if you have some way to explain that we observe minimum mass in the
yeah, we never get anything that low. We start out with masses that are at least 1.1 solar masses.
Okay. Is there a physical reason that...
Well, in this context, it's the Chandrasekhar mass that collapses. And a lot of that mass is buried in the inside. The supernova is a phenomenon of the envelope of that inner core, the envelope of the Chandrasekhar mass. The inner material is left behind, and it's very difficult to eject that material. It's very bound. And if you radiate neutrinos of any significant magnitude, then you make it even more bound. The reason the supernova works is because you're not ejecting the inner material. You're ejecting the envelope, the mantle, the outer material of the core. And that's not as bound. So you can leave behind your problems. And unfortunately, your problems include that half solar mass and solar mass.
Okay. And I also would like to ask about the fundamental mode you observe in your gravitational wave spectrum. And I see that this the frequency increases with time. I guess that this is related essentially to the increase in the average density, but I would like to know if you can see more physical effects in this variation, something related to the equation of state, for example.
Yes, the equation of state, again, if we look at the equations of state that still survive, that are still viable experimentally, they're still pretty close. And it's not so easy to distinguish those equations of state. I'm going to get back to here. And so you can see the differences are in the frequencies aren't that large. But you're right, the increase in the frequency is connected with the contraction of the core. And the F mode is a combination of a pressure mode and a buoyancy mode. It has some G mode character and some P mode character. And the latter is connected with the sound speeds. There's a little bit more to it, but by and large, it is directly connected to the evolution of the protoneutron star, its shrinkage, and the frequencies will generically go up. And you can show that approximately with the mass of the object, but inversely with the mass of the radius squared, approximately, radius cubed. It's something like that, square root. So yes, what you're seeing in this evolution of the frequency is the contraction of the core, and it's directly connected to the average density and this sort of thing of the object. There's going to be a lot more to disentangle all this. What you want to do is to analyze the neutrino emissions at the same time. And if you can infer the rate with which energy is being lost from the core, and a few other things, you can actually use those data to then analyze the gravitational wave signature. The best way of doing this would be an analysis of the neutrinos plus the gravitational waves in a large theory simultaneously. And that will be justified when we get really good data. but it's not going to be easy. Does that help?
Thanks.
Okay, so we have one more question.
Okay,
Last
my question. Thank you.
by George.
Okay.
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 Okay. Because I thought George had a question because his hand is
Yes,
raised.
I have.
Sorry. Go ahead.
Sure. Well, okay. Let me start saying that the thing of breaking a symmetry, which is essentially spherical initially, but not producing a totally spherical remnant is quite interesting. I'm not sure that this is one thing. So the use of the spherical symmetry breaking in a classical sense is okay. It's quite amazing. It's not something related to an initial symmetry, as Antonio Mario pointed out, and so on. The other thing is that you referred to the outcomes of the simulation somewhat as chaotic, and then I'm not so sure that you can use that word. You mean essentially that the outcome depends a lot of details in the pre-supernova and details in the convection and many other sorts of things. Is that correct?
Well, not quite. It does depend on the details, but because you have turbulence and turbulence is chaotic, there is a sensitivity to initial conditions.
Well, if you use chaotic related to the development of some sort of turbulence, which is still to be seen which kind of is it, which is related to the observation by Reynaldo, then I agree. But there's another way of thinking of that term chaotic, which is something that other groups have been finding, and I find extremely puzzling. That's the intermittency between the formation of neutron stars and black holes. Whereas naively, you would expect that at some threshold, at 50 solar masses or 30 or whatever, then you find you do get run out of energy for the explosion, and then you form black holes. But you seem to, to be reluctant to stick to that interpretation that the formation of black holes happen at smaller masses. Would give you your thoughts about what the intermittency reality, which is, or is rather an artifact of the way the things are handled.
Well, you're right that people use that term differently. I meant it in a technical sense.
Yes.
When you have turbulence, it is chaotic. It is dependent. The details depend on the initial conditions exquisitely. But the evolutionary community, the people who evolved massive stars, were seeing that their profiles, such as this profile here, were not monotonic functions of the progenitor mass. And they were seeing variations where you could go up in mass, but it would look like it was going down in mass if you looked at the general trend. And they couldn't predict for any particular mass exactly what the profiles would be. Now, they have convinced themselves that that their calculations are in fact really chaotic, in the sense that there is you can change the mass of the progenitor by infinitesimal amount and change the structure by a lot. And that was one of the reasons I showed this. This is changing the mass by 1/100th of a solar mass. And you see that one of the profiles looks like this, and the other profile looks like that. And that's fairly different. So this type of behavior to the evolutionary model community was considered chaotic. The degree to which it actually is real chaos is not clear, but it does look like it. It does look like it. And remember that they're doing evolutionary models in spherical symmetry with a fake mixing link theory. Nature has convective zones, which will naturally give you some degree of chaos. whether it's as large, it translates into as large a variation in the profiles of the density, for example, versus mass or radius is not clear. But when we did our simulations, these profiles were different enough that the net outcome was explosion in one case and not explosion in another. That was qualitative. So what I am saying, though, is different. What I am saying is there could be chaos in the initial models, but since there is turbulence in our context, even if there weren't any, if there were a smooth variation in progenitor structure that we would inherit, we would still get a range of outcomes naturally because of the natural chaos. The explosion will be earlier or later. It may be in one direction more than in another. There's going to be a little bit of rotation, maybe epsilon, and that's going to make some slight difference. What I don't know is the degree to which, I don't know the sigma of that. I don't know the mean and sigma of such a thing. That is something that I haven't really gotten grasp of. But what we do see is there is a fair sensitivity to the initial mass in the progenitors, and that's what the progenitor people have seen. And then given a progenitor, there is some sensitivity as we change little things to the outcome that seem to be chaotic in their nature with the real definition of chaos. So I think that what you're reflecting is that the field is still in chaos, but is hoping to emerge soon. And what we'll see is TBD.
Yeah, well, but finally, then this is very important because the possibility of forming slow mass black holes, or rather huge mass black holes in the sense of 15 or 20 solar masses, in the middle of progenitors that should explode otherwise, it will affect a lot the distribution and the problem of the so-called mass gap, which gains a new twist. The idea that the mechanism itself does not allow something between 2 something and 5 solar masses.
What we've published is that most of the models from 8 to 20 solar masses explode, and even up to 25 solar masses, according to the progenitor models we've inherited. But there are still a few that don't. And in one set of models, the 13 and the 15 didn't explode. In another, the 12 and the 15 didn't explode. And we know why, because it was the profiles we inherited. And it wasn't kicked at the right time into explosion, but it was marginal. It was really close. And so little changes made a difference. But most of those at lower mass would explode. What you're referring to is some models using 1D fake explosions, where they use something called a compactness parameter to
mainly yes, yeah, sure.
Determine on the basis of that compactness parameter and a condition for explosion whether you leave behind a neutron star or black hole. I think those calculations in those papers are completely wrong.
Okay, fine. This is so there's still the possibility. You don't have a certainty, but you have still the possibility of having a real threshold for the formation of astrophysical black holes around 20 or 30 or something.
Statistically.
Statistically, yes.
It's possible that there are a few black holes formed from the lower mass progenitors. And I think that it's possible there are a few neutron stars formed from the very highest mass progenitors.
Yes, okay, thank you.
But there is statistically a separation. But let me make the final point, which is connected with your question, which is they use this compactness parameter, which is the degree to which this slope, for example, here, is shallow or steep.
Yeah.
And if it's steep, it's low compactness, and they're saying these generally like to explode. What we find is these like to explode and these like to explode. These actually have a large accretion rate. And so the shock stalls, you have this big accretion rate, but large accretion gives you large neutrino luminosities, and it also gives you a large amount of material behind the shock. And what you get in the power of this deposit is the luminosity of the neutrino times the optical depth between the shock and the neutrino sphere. So it's L times tau. and you get a larger tau and a larger L, you have the shallower profiles, and those are the high compactness. And those high compactness ones are those that these groups say don't explode. And we see just the opposite. They're the most explosive. They just explode a little bit later.
Yes.
High energy explosions. It may well be that you'll get to a point where it might explode, but there's just too much binding energy to overcome on the outside. Those shallow profiles imply that there's a lot of binding to overcome, and that may be just too much, and you get a fair amount of fallback. The whole issue of fallback and when is an open question, because some of that can be on late time scales. But the idea of using the compactness parameter in the way these people have in an explosion condition, I think it does not take into consideration the progress that's been made in the last few years.
Okay, yeah. So, okay, they're intrinsically 1D and based on binding energy considerations. Okay, I see your point. I believe that's very important to open up the window for 3D and multidimensional effects that are really makes a lot of difference. As you sense.
And
thank you very much.
Resolution as well of the simulations, right? And resolution, because as you showed,
yes, that's another thing.
In the past, you had these failed explosion events, and exactly, the resolution.
No, the higher resolution generally makes it easier. We see, but we haven't done an exhaustive study. We just did one paper doing this comparison. It's not cheap. I boast that we can do a lot of 3D simulations, but at high resolution, it's problematic. So we could do a few of those.
Okay, thank you. That's all. Thank you.
Okay, Richard, maybe we can stop the YouTube transmission now. Or is there any further questions?